Hey, good morning. I'm continuing to do lectures on different types of excipients that are typically used in solution dosage forms. This is Jerry Nasamoni checking in from San Diego, California. It's so pleasant and nice here. Sorry to tell you that. I know um, this is extremely nice. Beautiful sunlight, a little breeze right by the sea. Haven't had an opportunity to go out and enjoy much at all. There's been a lot of meetings that I had to go to, but I've been able to see how things are from the car that I've been driving around, accompanied by Frank and Tanvi. But I really miss you guys. I really miss the classroom. I really want to come out there and interact with you guys in the classroom setting. And so today I got a few hours break in the afternoon, and so back in the hotel room recording these lectures. Anyway, it's great to connect with you guys. I hope you had the chance to review the earlier videos, both calculations and pharmaceutics lectures. We're going to continue um, on the topic of different excipients that I used. The earlier video was on preservatives. Today, this lecture is on antioxidants. So here are the learning objectives associated with this lecture. We'll start with definitions as usual. Oxidation reduction reactions. You know this. Typically, it involves transfer of one or more oxygen atoms or hydrogen atoms or electrons. The reduced form typically gets converted irreversibly to the oxidized form with a loss of n number of electrons. That's what this equation means. There's a particular type of oxidation reaction that is called autooxidation. This is of the most concern as far as pharmaceutical solutions are concerned. These autooxidations occur spontaneously under normal conditions without actually even adding a reagent or anything additional to these solutions. These occur under normal conditions of preparation, packaging, and storage. And then free radicals are chemical species that are of importance during oxidation reactions. And these chemical species contain an unshared electron in its outer shell that actually can contribute to its higher chemical reactivity and higher chemical potential. And it tries to, equilibrate by sharing the unshared electrons with other atomic species. Antioxidants, the topic of today's lecture, these are substances that prevent or inhibit oxidation. These are added to dosage forms that are prone to oxidation. As opposed to antioxidants, chelating agents are organic compounds that can form complexes with metal ions that actually have been found to play a role in oxidation reactions. So chelating agents inactivates metal ions that catalyze oxidations. As far as use are concerned, these are added to antioxidants are added to dosage forms containing components that undergo oxidation. Compound preparations, particularly susceptibility of ingredients, type of dosage form, site of application, storage conditions, beyond use days. All of these will have to be considered when trying to choose an appropriate antioxidant. Now, as far as autooxidation is concerned, you need to understand various mechanisms through which the autooxidation process occurs in dosage forms, because the utility of several antioxidants to prevent autooxidation actually to prevent how they prevent autooxidation is through actually its action or its activity to prevent one or more of those mechanisms involved. So typically, autooxidation proceeds through a series of three reactions, starting with initiation, propagation, and ending with termination. So initiation is typically catalyzed by heat, light, or metal ions. The initiator gets converted to R dot plus H plus. R dot is the free radical. as is shown in this equation. Okay, now once R dot has formed, it provides adequate opportunity for the next step to occur during autooxidation, which is propagation. So propagation occurs through combination of R dot with oxygen to produce RO2 dot, which is actually a peroxy radical. The peroxy radical during the propagation step, when it's formed, reacts with another molecule of RH, which could be the drug molecule, to form ROOH and another R dot. And so you can see this R dot that can feed back into the first step, and this process can continually lead to degradation of the active ingredient through oxidation. So that's propagation. The process of autooxidation is being propagated by continual generation of R dots or free radicals. Now, termination can be through a combination of two peroxy radicals to form stable products, or a peroxy radical and another free radical to form stable products, or combination of two free radicals to form stable products. Each of these can lead to eventually formation of stable products that can actually terminate the process of autooxidation. So these are the three steps that are involved in autooxidation. So we'll now start off with different types of antioxidants and how and where they affect during to prevent the oxidation process in dosage forms. We'll start with chelating agents. These are agents that inhibits oxidation by chelating metal ions that acts as catalyst during the oxidation process. And the metal ions that we're talking about here include Fe3 plus, Cu2 plus, cobalt 3 plus, nickel 2 plus, and manganese 2 plus. Even the presence of these metal ions in very minute amounts can actually have an impact on the autooxidation process. And this is of particular importance because even the highest quality, highest purity excipients and ingredients tend to have trace amounts of these heavy metals. So even when using the highest quality ingredients, you may have to use some sort of chelating agent to prevent these heavy metals, or sorry, not heavy metals, these metal ions from catalyzing autooxidation. Some examples for commonly used chelating agents in dosage forms: EDTA, citric acid, and tartric acid. These three chelating agents are most commonly used, very widely used as chelating agents in dosage forms. The binding capacity of these three chelating agents are dependent on the pH of the solution. That's because, if you note here, that's acid, that's acid. This is actually ethylene diamine tetraacetic acid. So all of these compounds are acidic, and so the binding affinity, binding capacity is highly dependent on pH, and the degree of ionization of the degree of ionization of these organic acids is going to be pH dependent, and typically these three chelating agents are most effective and fully ionized. And so you know that these three are organic acids. They probably have COH functional groups whose pKa is 5, and so a pH of greater than 5 will lead to presence of these molecules to a greater extent in the unionized form, and hence the utility of these chelating agents will be most prominent when the pH of the final solution is greater than 5. Now, the mechanism of action of antioxidants. The antioxidants typically can act through preferential oxidation. That means these antioxidants can easily oxidize when compared to the active ingredient that you're trying to protect. These antioxidants that undergo preferential oxidation tend to have lower oxidation potential than the drugs that they try to protect, and hence these molecules undergo oxidation much faster and quickly than the drugs, and thereby protect by getting preferentially oxidized. These types of antioxidants are also called as oxygen scavengers because they are capable of being oxidized faster. Examples of this category include sulfites, ascorbic acid, monothioglyscerol, and sodium formaldehyde sulfoxylate. Another type of antioxidants, they act by functioning as chain terminators. That is, these molecules provide readily available hydrogen atom or an electron. They get converted to less reactive radicals, which are more stable. They combine with other radicals in the termination step, providing an opportunity to prevent the drug molecules from being oxidized to stable oxidized products later on. There are two different categories of chain terminators that are utilized in pharmaceutical dosage forms. Oil system antioxidants, which include ascorbyl palmitate, butylated hydroxyanisole, butylated hydroxytoluene, propyl gallate, and tocopherol. Something that is a common factor between these agents, these antioxidants, that they are all oil soluble. As opposed to the water-soluble antioxidant monothioglyscerol, because of the presence of this polar moiety in this antioxidant glycerol, this is water-soluble as opposed to the other. The utility of these is that you have to choose appropriate antioxidants. So if you're dealing with an oil-type formulation, then you better choose an antioxidant that is oil-soluble. Otherwise, it's not going to be effective. And another mechanism through which antioxidants exert its effect is by functioning as reducing agents. They are able to reduce an oxidized drug or component. Some examples include ascorbic acid and sodium thiosulfate. Some properties that are ideal as far as antioxidants are concerned: these should be effective at low concentrations, should be stable over a wide pH and temperature range. This is of importance because, temperature, how warm, high temperatures could be used during solution, when preparing solutions, and hence antioxidants should not be degraded or be affected by temperatures that are used during processing. Should be stable over a wide pH range because being solutions, buffers may have to be used. Particular pH may have to be used during preparation of the solution because the drug may be soluble over a narrow pH range, and this will have to be taken into account. And so antioxidants that are used in formulations should be stable over the pH range that the solutions are going to be used as. They have to be have good solubility in solvents that are used in the preparation. Should be physically and chemically compatible with other formulation ingredients because of the fact that these antioxidants, if you go back and refer to the mechanisms that were detailed in the earlier slides, they all are reactive, chemically reactive chemicals. Which makes them prone to chemical reaction with other ingredients that are used in the formulation. So you have to appropriately select these agents, and they have to have excellent compatibility with other ingredients. Additionally, since solutions could be used as oral formulations, the antioxidants should be free from objectionable odor, taste, or stinging. Should be colorless in both the original and oxidized forms, and that's because of the fact that oxidizing agents or antioxidants typically that are not used in pharmaceutical formulations. There are numerous other examples for these types of agents. They actually, when they get reduced, they have a different color, and when they get oxidized, they have a different color. But the type of antioxidants that are used in pharmaceutical formulations should not show such drastic color change, and they should be preferentially be colorless, because otherwise it can affect the color and the pharmaceutical elegance of the final product. Should be non-toxic and non-sensitizing both internally and externally. Should be of proper cost. Should be compatible with the containers and closures. These antioxidants should not absorb or adhere or otherwise react with the containers and closures, in which case they actually will lose its antioxidant potency and will lose its effectiveness in a formulation. Examples for different types of antioxidants that are listed in the USP/NF are shown there. Review these chemicals. Make sure that you're familiar with these. These are very commonly seen in the list of ingredients, particularly those solution type formulations contain one or more of these antioxidants. Chelating agents that are listed in the USBNF include calcium sodium disodium edetate, a calcium sodium salt of EDTA, disodium edetate, which is a sodium salt of EDTA, edetic acid as itself, citric acid, and tartaric acid. Antioxidants that are capable for use in aqueous formulations. Ascorbic acid is perhaps a very commonly used example. Ascorbic acid is an organic acid. It's very soluble in water. Its effective concentration is 0.05 to 3%. The mechanism of action of this antioxidant is through its capability to act or perform as an oxygen scavenger. Other examples for antioxidants used in aqueous systems include sodium bisulfate and sodium metabisulfate. The mechanism of action of these two agents, these sulfur-containing agents, is as oxygen scavenger. However, it should be noted that there are several warnings related to use of these agents in pharmaceutical preparations. These have been found to be highly prone to produce allergic reactions. A warning label is required in formulations that contain these sulfite type agents. These have been found to produce anaphylactic symptoms. That means anaphylactic symptoms are instances where the body actually responds by producing a large amount of agents, biochemical molecules within the body that leads to severe and drastic reduction of blood pressure, number one, and number two, will produce severe inflammation and swelling of the respiratory tract. These two combinations, in combination, the severe and drastic drop of blood pressure combined with inflammation of the respiratory tract will cause life-threatening asthmatic episodes, and particularly patients who suffer from asthma are more susceptible to these reactions, and hence should be warned and should be prevented from using products that contain these type of agents. Sodium thiosulfate and sodium formaldehyde sulfoxylate are other examples for antioxidants that can be used in aqueous systems. Sodium thiosulfate is actually a reducing agent. Sodium formaldehyde sulfoxylate is an oxygen scavenger. Now, moving on to antioxidants that are used for oil systems. An example is ascorbyl palmitate. Although ascorbic acid is a water-soluble antioxidant, ascorbyl palmitate, which is actually a derivative of ascorbic acid in combination with palmitic acid. Palmitic acid is a straight chain fatty acid, has a long chain of carbon atoms. It is not soluble in water. It is more soluble, or rather soluble easily in organic material and oils. And so it's very effective in our concentrations of 0.001 to 0.2%. And the mechanism of action of this compound, ascorbyl palmitate, in oil-containing formulations is through its effectiveness as a chain terminator. Very commonly used antioxidant in oil systems. Two very common examples are listed here: BHA, butylated hydroxyanisole, and butylated hydroxytoluene. These two are abbreviated as BHA and BHT respectively. It occurs as a white or pale yellow powder with a faint odor. It is insoluble in water. However, as you can see, it is soluble in different types of organic solvents as well as fats and oils. The effective concentration is very low. BHA can be used at a very low concentrations of 0.005 to 0.01%, and BHT can be used at a very low concentration of 0.1%. So these two can be used in very minute amounts, but still can exert its antioxidant effect, and so these two are very, very commonly used in oil-containing formulations. And the mechanism of action of this type of antioxidant is through chain terminator. Two other commonly used antioxidants in oil systems, propyl gallate and alpha tocopherol. Alpha tocopherol is another name for vitamin E. Both are oil soluble and are very effective in very low concentrations. Propyl gallate is effective at 0.005 to 0.15% concentration, and alpha tocopherol is effective at a concentration of 0.01 to 0.1%. Both exerts its effect as antioxidant as a chain terminator. Then chelating agents commonly used are EDTA and disodium edetate. Both are effective at very low concentration of 0.1%. Calcium disodium edetate and citric acid both are also very effective at low concentrations. Calcium disodium edetate is effective at 0.1%, and citric acid is effective at 0.322%. Tartric acid is also another example for chelating agent. All these chelating agents that are listed here are very good and soluble in water, as is shown in the slide. That's the end of this lecture. Fairly straightforward and simple lecture. Things to note as far as this lecture is concerned are names and their utility in different types of formulations, whether these are used in water formulations or whether these are used in oil formulations. Additionally, an idea about what kind of mechanism these antioxidants used to function as an antioxidant is important, and some idea about the different mechanisms that are used, the detailed explanation of how autooxidation occurs in formulations is also of importance. Very straightforward and simple lecture. Do not memorize the numbers and the percentages. You don't have to memorize those numbers. What is the solubility of particular solubility in terms of numbers, but you will need to identify broadly examples for antioxidants that can be used in oil formulations, which will be more oil soluble. I'm not going to ask you to exactly remember the solubility number in terms of how many grams or how many milligrams will be soluble in oil. No, but you need to broadly know what kind of compounds are oil soluble and what kind of antioxidants are water soluble. Okay, that's the end of this lecture. Thank you for your attention, and I will post more lectures soon.